Thank you, Brian. See, this is what can do to you. Thank you, Brian. See, this is what can happen to you if you're a grad student and you do a theory, and then, after writing all these theory papers and you have lunch with all these observers all the time, you think, oh, actually, maybe we can do this. And then everybody knows you for this one observational thing you've done. And I don't know what this says about my theory, or I don't know. So you'll get to decide. But actually, we were very fortunate. The hardest thing about this project was actually to convince the people at Space Telescope that we could do some unique science with the fine guiding sensors, with which basically storage just is engineering data that nobody else had thought about or done before. But once we had convinced them, it was easy sailing from there. So this is a lesson. Always have lunch with interesting people and brainstorm crazy ideas, because occasionally you come up with something that nobody else has thought of because you never had lunch in that funny combination before. So, okay, but today I'm going to tell you about something different. It's going to be actually mostly theory, although I do still occasionally I do tons of observations, but my heart is with theory. And so I'm going to tell you a bit about the formation of planets in our own solar system and around other suns. And before I start, I particularly would like to acknowledge two of my collaborators. One is my first graduate student who finished about a year ago, Niraj Nanda from MIT, and Sivan Ginsburg, who is currently a graduate student at the Hebrew University, but he is going to finish next summer, and he's currently applying for postdocs, and he's truly exceptional. So if you see his name, take a good look at his application. So I thought, before I bombard you with all the new things we've discovered and we think of how extrasolar planets and our solar system formed, I first give you sort of an idea of how, in a nutshell, we think planet formation proceeds. So this is sort of the back of the envelope, 5-minute version of sort of a year-long course on planet formation. So what we think, and in case you haven't noticed, you should probably try to look at this slide because this one has the button cut off. But just, so how do we think planets form? Well, of course, when stars are forming, they're forming from a collapsing cloud of gas and dust. Because of the axis angular momentum, they tend to form with disks around them. These disks consist mostly of gas, but they do have some dust in them, roughly 100-to-1 in terms of mass ratio. And with time, the dust settles to the midplane. And in this midplane, we start to form the first planetesimals. These are the building blocks of planets. And actually, how precisely these planetesimals form is something we still argue about a lot. We have some ideas, and some parts of the growth work really well, but there's still some obstacles. So I'm not going to spend a lot of time on this today, but I'm just going to tell you we're going to form these planetesimals. We think once we form them, they're about 1 kilometer in size, possibly bigger, but that out of magnitude. The thing is, the problem becomes much simpler once your building blocks are 1 kilometer or bigger, because when they're at 1 kilometer, they're large enough that we can just, to first order, ignore the gas. And if we want to understand the dynamics, the growth, the collisions, to first order, it's just a gravity problem. And gravity, of course, is much easier than having to account both for the gas and gravity together. So then what's going to happen next is these planetesimals are going to meet each other and collide. And because the relative velocities are low, they will start to grow and stick. So you start to form larger planetary embryos. The very first stage that we can sort of identify that's sort of important in the formation of planets in the growth process is something that's called runaway growth. So why is it called runaway growth? It's called runaway growth because the rate at which something grows or doubles itself in size or in mass, so the dr dt, 1 over r dr dt, is proportional to size. So what it means is the bigger you are, the faster you grow. So this actually exists in many cases in nature, like in some chemical reactions or some biological systems. But basically, once you're a little bit bigger than everyone else, you're going to get bigger still, faster than everyone else, and so you physically, in size, are going to run away from the rest of the population. So why does this happen in our disks? It happens because the physical cross-section for a collision is actually enhanced above just my cross-section because of gravity. So we get something that's called gravitational focusing, right? If two objects are approaching each other, if they're going slow enough, this guy here is going to feel the gravitational pull of the accreting planet, and I can focus it towards it and accrete this body, although it's not coming on a collision orbit head-on originally. And that's gravitational focusing. And that works as long as the velocity dispersion is less than the escape velocity from the body that's doing the accretion. And so this is why when we look at this rate here, we have the escape velocity in here. And so if you assume that the background velocity of the small bodies is independent of the size of the large ones, the escape velocity scales as the radius. So you have a radius squared in here. And so then this whole expression is proportional to size. So that indeed means that the bigger you are, the faster you grow. And so in planet formation, so why do we care? Why is this important? It's important because when you try to form planets, it's always a race against time. And why is that? It's because you need to form the cores of Jupiter and Saturn before the gas disk goes away. And we know very well from astrophysical observations that gas disks stick around only a few million years. So we know we need to form something like Jupiter, and even more strongly, we need to form a core that can accrete all the gas to form a Jupiter within a few million years. And so although runaway growth is not very good at converting most of the mass in really big objects, it's crucial for forming the first sort of big planetary embryos that can form your Jupiter. What's even cooler, because I love the Kuiper belt so much, is the fact that when we look at the runaway growth, it turns out that our own Kuiper belt probably got stuck right in this growth phase. And so we can actually study this phase really well by looking at the size distribution and the mass distribution in our own Kuiper belt to learn more about planet formation that we couldn't learn from the fully formed planets today because they don't keep that relic of this intermediate stage. But enough about runaway. So what's going to happen next? So you're going to grow bigger and bigger embryos until they're so large that they are gravitationally completely dominate their own food, their own feeding zone. So what happens is that this guy here will gravitationally dominate all the motions of these little guys here that's still growing, and then you form another embryo a little bit further radially outward. And we call these guys oligarchs. And so you can ask yourself, well, how big of a body can you grow? How big of a planet do you get if you simply grow by accreting all the material that's available in your feeding zone? And it's a really simple calculation, right? You simply have to add up 2 pi times the semi major axis times the width of this feeding zone and multiply it by the mass density in your disk and solids to find out how big your body will be. So we're just adding up all this material. How big is the feeding zone? Well, it's simply the distance over which the gravity of the planet, right, dominates over any tidal forces from the sun. So anything can be accreted onto the planet. So we call this thing, in the planetary context, usually the Hill radius, but you may know it also in terms of the Rush lobe. So the Hill radius for the Earth is around 200 times the physical radius of the Earth, and that's the distance up to which you can have a moon, right? You can't have a moon beyond that because the tidal forces from the sun would dominate and the moon would have to orbit the sun instead of the Earth. So anyways, if you stick this Hill radius in here, and you do this calculation for the outer solar system, what you get as an isolation mass is actually the mass of Neptune. So it's fantastic, right? So Uranus and Neptune, to very first order, probably formed as planets by simply accreting all the material in their respective feeding zones. So then we can go back and repeat this in the inner solar system at 1 AU or 1.5 AU. And exactly the same calculation gives you about the mass of Mars. So this is fantastic if you want to form Mars. However, it's not quite so fantastic if you want to form the Earth, because, of course, Mars is more than a factor of 10 less massive than the Earth, so not quite so great. So where did we go wrong? Well, we probably didn't go wrong anywhere. What this tells us is that actually Mars is also likely to be an isolation mass, but that for the Earth and Venus, there was an additional stage of assembly during the growth process. And of course, you probably all know that we call this the giant impact stage, where basically you have a collision of dozens of these mass-sized embryos that basically eventually lead to the formation of the Earth. So why do you have these giant impacts in the first place? Well, what is happening is once the planetary embryos accreted most of the planetesimals, there's no more strong damping for them. So they gravitationally start to excite each other. They excite the eccentricities, and the orbits start to cross, and you end up with having a series of giant impacts. Only once you've concentrated most of the mass in 2 or 3 bodies that are well separated in space can your system again settle into long-term stability. And then there's a last stage that's often ignored, but it's actually sort of important to explain our solar system, which I call the cleanup stage. In this stage, basically, your planets just accrete all the leftover planetesimal material that may have been ejected during the giant impact phase. What's really cool about this very last stage is the fact that A, it's needed dynamically, because as you can imagine, at the very end of the giant impact phase, our orbits are not going to be nice and circular, right? I had to have crossing orbits to have my collisions, so the end product I get of that stage is not going to be nice and circular, what we have today. But what a small amount of these leftover planetesimals can do collectively by something which we call dynamic friction, which you may know from, at least the astronomers may know from galaxies, they collectively can damp the eccentricities close to circular before they're being accreted. So this is great. What's even cooler is that we actually have geochemical evidence for this accretion after the moon formation. And that's, that comes from what we call highly pseudophile elements. So that just means these are ion-loving elements. Examples of those are iridium and osmium. And we find these elements, the fact that we find these elements on our Earth mantle is interpreted that as them having been added to the Earth after core formation. Because if these materials had been added to the Earth before the core of the Earth had formed, so before the last giant impact when everything was molten, these things should have ended up in the Earth core with the ion, because they're ion-loving. They would love to be with the ion. The fact that they can't be with the ion means that they probably were sprinkled onto the Earth or accreted onto the Earth after core formation finished, hence after the giant impact phase. And that's kind of great because you can infer that about 0.5% to 1% of the mass of the Earth was accreted in this late stage. And beautifully enough, this is enough to sort of circularize the orbits to the level at which we see them today. So that's sort of, in a very simple nutshell, on how we more or less think the solar system formed. So all was good and happy. And then, of course, all these extrasolar planetary systems came along. And of course, it would be crazy for me to even try to give you a full summary of this field. But I'll give you a brief summary for what's relevant for today and for this talk and what motivates a lot of our work. So there was, or there is, this fantastic space mission called Kepler. I'm sure one way or the other you've heard of it. And basically, it was a very simple science experiment. All it does is it's a space telescope that was launched in 2009. It's monitoring about 100,000 stars continuously, the same patch in the sky all the time. It's like super boring, right? One of the most boring experiments you could do. And it basically integrates the light over 30-minute intervals. And what it does is it basically tries to catch the dimming of a star as a planet transits in front of it, blocking some of that light. That's all it does. And actually, really to call something a detection or a candidate, it needs to have seen this planet transit at least 3 times. So when we see this dimming repeat 3 times, you get the period, and you also get the size of the planet, at least relative to the size of the star, because you know how much of the light has been blocked out. So this rather simple experiment has been a huge success. And actually, this goes back to my KBOs. The method is essentially the same, just a different geometric optics regime, right? In my KBOs, oh, you don't know this, but the KBOs that we were looking for were in the Fresnel diffraction regime, so the light curves look different than the transiting planets, but the experiment is essentially the same. And so Kepler discovered this humongous amounts of planets, and it was a huge success, but we didn't anticipate this at all. And why didn't we anticipate this? I'll try to show you here. So the planets, this is an already, again, out-of-date diagram, but all these blue points correspond to one of the planetary candidates that has been discovered by Kepler. What I'm showing you on the x-axis is the period, and on the y-axis is the radius scaled to the radius of the Earth. So every blue point is one of the Kepler candidates. There are more than 4,000 known. And then for comparison, I've plotted here our solar system. So this is Mercury, Venus, and the Earth. And in addition, here, this red line corresponds to the radius of Neptune. So what does this plot tell us? Well, one thing that is extremely striking is the fact that there exist all these extrasolar planets in a phase space where we don't have a single one in our own solar system, right? Our closest planet is Mercury at 90 days. And there's nothing inside. Whereas most stars actually have these close-in planets. Furthermore, most of these planets that sort of live in the terrestrial planet region in our solar system, in these extrasolar systems, they're much bigger. They tend to be in size, at least so far, between Earth and Neptune. So although, actually I should also tell you that there's this big empty region here. So this could mean two things, right? It can mean that solar system analogs are really, really rare, or planets like our terrestrial planets are really, really rare because this region is empty, or that we haven't yet been sensitive enough to actually find them. And in fact, right now, this is the reason. So the reason this region here is mostly empty is that for most stars, we haven't actually been sensitive enough to try to find true Earth analogs. So I can't yet tell you how much of a freak our Earth is or Venus is. But what I can tell you with certainty, and it's sort of slightly mind-boggling, is that more than 50% of all stars in the night sky have one of those super Earths or mini Neptunes, as we call these planets, in orbit. So we're already a little bit funny that we don't have one of those guys. So these are super ubiquitous. They're currently the most common planets that we know of. We may find more and smaller ones, but for now. So they're the most common planets in the universe that we know of today. Yeah, of course.
Is there a version of the star normalized to the sun? I mean, these planets presumably are orbiting
other stars, yeah?
other stars, and so is there a way of quantifying, I mean, we are rare, but maybe our sun is rare too, I don't know.
So,
in the context of this.
so the stars were collected that they were sun-like as much as they could.
So they all sun-like.
There's still a large fraction of M dwarfs in there, but they're G and K dwarfs, most of them, the vast majority. So they have similar separations from the sun and similar equilibrium temperatures. It's true that some of the most exciting planets in the sense of whether in the habitable zone have been found around M dwarfs, because M dwarfs are not as bright, so the habitable zone is closer in, and it's easier to find planets closer in, because basically if you have a fixed observing period, in this case 4 years, you'll get to see them transit more often, and hence you can find smaller planets, right? This is why there is this trend here. So this is why you may have, yeah? It's possible, right? So yeah, so it's very possible that there are many, so right now 50-50 is not yet rare. So it's exactly the question you would like to ask. So right now I can't tell you anything how common Earth-like planets are. Then you can ask the question, how common is the solar system, or something like the solar system? And there's a 50-50 thing right now, because we do not have one of those planets in our system, and we know that. There's no question about that. Then you could ask the question, how you define solar system. If it means having a Jupiter at 5 AU, we know that only about 10% of all systems that we surveyed have a Jupiter at 5 AU. So that would put us in the 10%. Depending on how exactly you define us or what question we want to.
That also depends on the observing time.
Say again?
Finding Jupiters depends on the observing time.
Yeah, exactly. So this is what they corrected for in the 10%. Yeah, so they come actually from radio velocity surveys, but it's okay because radio velocity surveys have been looking for extrasolar planets since the 90s, or actually even slightly before. So they actually are sensitive to planets that are out at 5 AU, or actually further, because usually you only need half of the period. But it's a good point, and that's actually why my plot here for the Kepler planet sort of cuts off at basically a year, because Kepler was a mission that lasted about 4 years. If you want to see something, a transit repeated at least 3 times, you sort of limit it to this 1 AU, to this. And so the transit method is actually not a great way right now to constrain the longer period planets, because we wouldn't have seen them transit more than once. Yeah, I know. I always get asked about this, and you're right. There's a cluster, but I think it's a bias in the in the detection algorithm of the way they pulled out the planet. So there's some instrument systematics, because so the way that Kepler works is it's always staring at the same patch, but it's rotating around its axis. So that means that a given star or a given planet will be on a different CCD over every 90 days. And that induces some biases in the data, and I think this somehow managed to manifest itself as this funny cluster there. I actually don't think any of these are real. But if you just go ahead and plot the whole reported sample, that's what you get. You can even see the finiteness of the radius thingies they reported, because you see how they all, of course, this is not real either. Okay, so great, or not so great. No, I think it's fantastic. So what does this mean? So I guess the question that I'm really interested in is trying to understand, how did these planets form? Where on Earth did they come from? How did they form? And should we think of them and their formation more like super versions of the Earth? So that's why some people call them super Earths. So, they're formed close to where we see them, with a phase of giant impacts, and somehow there was more material, and they just managed to do it a little bit bigger and better than we got in our solar system. Or maybe this is not the right way to think about them. Maybe they formed more like mini Neptunes, the mini versions of Neptune. They sort of formed at several AU, maybe even tens of AU. Just as isolation masses, they accreted all the material that was there. And then they migrated inwards. We know there was gas. We know they accreted some gas. And we now just see them in these inner regions, but they didn't actually form there. And we should really think of their formation more like Uranus and Neptune. Or, of course, there's always more than two options in life, unfortunately. Maybe nature was even more creative than that. And it was some sort of weird combination of these two. And that's sort of what we'd love to find out. So how did these planets form? What can we say with certainty? And what sort of do remain some of the puzzles? So I split up this talk in two parts. The first, I will want to focus on actually how these planets got the composition that they did. And a lot of this is a story about gas. So Kepler, if you see a transiting planet, all you get is really the radius and its period. So that's not an awful lot of information about a planet. However, so there are two parts. So it turns out that even with only these two pieces of information, in some cases this actually tells you a lot. Because in some cases the radii are so large that you know that this planet has to have some sort of gas as an atmosphere to explain a large radius. And so I'll show you an example here. This is a little bit of a cheat, because here we have masses also. But let's forget for a second. Say I don't know the mass very well. If you just plot the radius, if I have planets up here, there's no plausible composition I can come up with that consists of rock or iron or water even that could explain a radius that lies up here. So for any planet that has a radius up here, I know that it must contain a large gaseous envelope on top, whatever may be underneath. Furthermore, then for a subset, we do have mass measurements. And then, of course, you can do better. You can actually put it at a point up in this plot. And we can infer a few things about their composition. So how do we know the masses? So one way to know the masses is using the Doppler method. So you see the Doppler shift of the star for some of these transiting planets. So then you get the mass and the radius. In other cases, actually, I haven't told you yet, but more than 1,000 of these planets are in multiple planet systems. So all these planets are orbiting together their host star. And basically, many of them are so closely packed that they push and pull on their neighbors. So they actually dynamically perturb their neighbors enough that we can see this in the transit time. So when they transit, it's not exactly the orbital period, it's slightly offset in a sort of sinusoidal way, and you can actually infer from that the masses of the planets in the system. So it's sort of an indirect way to measure the masses, but it works very well. And it doesn't cost you any more observing time. It's just computational time, which is usually much cheaper. So then you can make a plot like this. So you can put down the planets you found with their masses and radii, and you can see that the masses are usually much more uncertain than the radii. And you can ask the first few questions about the composition of these planets. And you can already see from this plot, so there are some things, so if something would be made purely out of iron, it would lie on this black line here. If something would be purely made out of water, it would live up here. So theorists have great fun, right, constructing all these hypothetical planets that probably could never exist, right? Purely iron is probably as crazy as purely water. However, we can start to make models, and we get an idea. And you can see that there are several of them that do require 1 to 10% of the total mass to be in some light gas, and typically the one everyone's favorite is hydrogen and helium, basically because it's most abundant and would give you the biggest inflation for the radius. Otherwise, you would need even higher gas fractions. So I would like to remind us that this is extremely different from the atmospheres that we are used to, especially on Earth. So we do have an atmosphere, and it's super important, right? But it does not modify our radius at all, right? If we would find an Earth going around another star, it would perfectly fit on the right mixture between rock and iron. So we could not infer for an Earth that we observe from far away that it has an atmosphere this way. And that's because our atmosphere is important, but its mass is tiny, right? It's about 1/1,000,000th of the Earth mass is in our atmosphere. 1/1,000,000th, it's like nothing. And our scale height is less than 0.1% of our radius, right? It's nothing. It wouldn't change the radius that we see in any significant way. So these planets are different beasts. Here, they have so much atmosphere that it really changes the radius that we see. That's the only way where we can infer that they're there, at least right now. Okay, so then the question is, well, how do you get all this gas?
On those,
yeah?
On those big ones, you have enough there to do spectroscopy?
Yeah, so we're trying. So the problem is, and not that they're too small or too big, that many of them, because Kepler picked one patch in the sky, the average distance of most of the stars, most of the host stars of these planets are very dim and not very bright. And so it's very hard to do a spectroscopy or any real detailed follow-up because the host stars are not very bright at all. In fact, this is why there is this new mission called TESS that's going to be launched next year. And the main aim of that mission is to find planets around the nearest and brightest stars. So you could actually do really good spectroscopy and actually really learn directly about the composition of the atmosphere. Jupiter wouldn't be on this because its radius is way up here. So these are all these super Earths or mini Neptunes. So Uranus and Neptune is here, both here as a reference point. Yeah, and they're actually a good analog to some of those planets because if you look at them, right, Uranus and Neptune, to very first order, have about 10% of their total mass in hydrogen and helium. So they really look like Uranus and Neptune, only that these planets live not at all where Uranus and Neptune live. They live like very close to their hosts. So how do you accrete gas? Well, okay, so though these planets, as the cores are forming in these planetary disks, if you want to understand how much gas a given core can accrete, the first question is sort of pretty simple to answer, right? I have my star, I have my disk, I put down my core, and I can ask, well, how much of the surrounding gas is gravitationally bound to my planet? So I can go and add up all the material in the Bondi radius and sort of can call this sort of my atmosphere. So if you do this, you will never accrete 1% or so of your total mass in gas. And it's simply because the densities are not high enough and my Hill spheres at these regions are not big enough, or the Bondi radii are not big enough to give you a really significant amount of gas. So what happens next is the following. So once you accreted the first round, and this is sort of essentially adiabatic in structure, this envelope will start to cool and contract. So as this envelope starts to cool and contract, some of the heat will leak out here. Now there is some space in the outer region, and I can put more. I can accrete more gas from the disk. And so because of this nature, basically how much gas you accrete doesn't to first order depend on how much gas density you have in the disk, it depends most strongly on how much time I have to cool, because I filled up my Hill sphere, I need to cool the gas below so I can pile on more gas on top, and then again, the whole envelope needs to cool and shrink so I can accrete even more gas from the disk. So basically, we call this accretion by cooling. And so when you look at the envelope structure, what you get is, initially, you get a profile that's essentially adiabatic, but then if you wait a little bit in time so you can cool a little bit, you form an outer radiative layer that can radiate away any heat so you can contract, and that's connected at the radiative convective boundary to the sort of adiabatic inner regions where you have energy transport by convection. And so with time, you can then build a larger and larger radiative layer, and you can accrete more gas, and you can build up densities on the inside. And so then you can ask, okay, how much gas do I accrete? Now it's just a question of how long is the disk around, and basically you get something like this equation here. So this is the gas fraction, so the gas accreted divided by the mass of the planet. And you can evaluate this, and you can see that the first order, it only depends on the mass of your embryo, of course, because that determines how big is my feeding zone, how big is my Hill sphere, how much gas can I gravitationally hold on to, and then the disk lifetime, because that means how long is the gas around, over which I have time to cool and put more gas on the outside. And then the equilibrium temperature, just because it tells you how hot everything is to begin with, right, from the start. And of course the opacity, because that's sort of the bottleneck that determines how fast you can cool. And this is really the opacity at the radiative convective boundary, because this is sort of where your heat has to leak out. So what is cool is that this does not depend at all on the disk surface density. Or if you do this precisely, it only depends on it logarithmically. And that's because the radiative convective boundary is connected with an isothermal profile, which is like an exponential, to the disk. And so this is why you only get a logarithmic dependence and not linear dependence on the density. So this is great, because this means that I should be able, for these extrasolar planets, tell you how much gas they have accreted, right? Because I know their mass, or have a good idea. I know the equilibrium temperature from the star. We can make some well-educated guesses about the disk lifetime, and we have some sort of idea, at least, about the opacity. So, you tell me how big the core is, I tell you how much gas you get. Okay, but it's not quite as simple, because not all the gas that we just accreted is ours, or we don't get to keep all of it. And why is that? Because usually when people looked at gas accretion, they just stopped there and they said, we're done. Well, we're not done, unfortunately, because so eventually the gas disk will go away. So what happens? So the pressure support from the disk will go down. So you lower the density on the outside of your planet. And now the gas you have just accreted will start to expand back, essentially into vacuum. So this way, you will actually tend to lose between 25 to 75% of all the gas mass you just accreted as your disk is going away. As the disk goes away, it takes some of it with it again because of this pressure support loss. And because the inner envelope has enough energy that it has to release to cool to help move out the outer layer. So basically, as the planet tries to shrink and cool on the timescale in which this goes away, the inner layers shrink to a radius that's roughly comparable to the planet's radius on a very short timescale on which the disk goes away. And it can do that because a lot of the energy that needs to release because of cooling is basically lost together with the outer layers that are sort of blown away as the disk goes away. So this is actually important because that's the true initial condition if you want to understand the thermal evolution of these exoplanets. And this is really important, especially for direct imaging surveys, because we care about the luminosities, but that's then entirely determined by the accretion history and their mass loss history, because that will set the energy budget and therefore the brightnesses and luminosities of these planets. So are we done then? Not quite, because we can still continue with losing mass. So there are actually two regimes in which the planets will continue to cool. And that actually is determined entirely by what part of your planet is dominating the heat reservoir, the heat capacity. So in the first regime, the heat capacity is dominated by the planet's envelope. So this is true when you have, for a planet with a hydrogen-helium envelope and an Earth-like composition core, is roughly true when you have more than 5% of the total mass in the envelope. So Uranus and Neptune and Jupiter and Saturn are great examples of these. So in this case, the heat budget is dominated by the envelope, and with time, the envelope now will just shrink and contract over gigayear timescales. And actually, Jupiter is still sort of stuck at this stage, right? Jupiter is still shrinking. It's still releasing more energy than it's receiving from the sun. So it's still sort of in the late stages of this cooling phase. And so basically what happens to the envelope is here's the radius convective boundary, which essentially we can take as the radius of the planet. And that's moving inward with time as the envelope cools and contracts. So those planets are good. They're safe. We formed them. We accreted them. We can keep those gas masses. However, in the other regime, where you have about less than 5% of the total mass in the envelope, the story is different. What is different here is now the heat reservoir, the heat capacity, is actually dominated by the core underneath the envelope. And so what this means is once the envelope has shrunk to a radius comparable to the core radius, it now wants to continue shrinking. However, all the energy it's radiating away and that's released, so it should in theory be able to cool and contract, is now resupplied by the core underneath, because the core wants to cool too. And so if you have a lot more heat capacity, energy stored available for cooling in the core, what will happen is that the envelope will want to shrink and contract. However, all the energy that's radiated is resupplied from the inside. And so what happens is that mass loss continues because my radius cannot really shrink because I'm resupplying the heat that I just lost. And so I basically stuck at almost constant radius, losing my envelope over gigayear timescales. And what this actually means is if you are a planet that's closed in with an envelope that's only a few percent, you're going to lose that envelope over gigayear timescales until you're a bare, rocky core with nothing left. Is there anything that can save you? That's a pretty crazy statement, right? Because that means sort of we should only find planets that have envelopes that have more than 5% in terms of their mass budget in hydrogen helium, or naked cores, but nothing in between, right? Because I told you, the ones less than 5%, they have to lose everything. So the only thing that can ultimately save these guys is time. So the mass loss will continue, but it's possible, and especially if you go further away from the host star, that this takes gigayears, or even tens of gigayears. And so when you see envelopes that are a few percent, they may just simply be a few percent because your planet didn't quite yet have enough time to lose the remaining part. So, okay, so loads of modeling. Let's actually look at some data. So is this borne out? We can actually look at the radius distribution of extrasolar planets, of these super-Earths. And this is exactly what this plot is showing here. So this gives you the radius distribution of these super-Earths and mini-Neptunes. And you can see it actually does have these two tails, these two peaks with a tail here. So these gray things, the histograms with the error bars, this is the data. And then this green line is basically from this model. So you start off, you know the mass distribution because we have that information from large radial velocity surveys. I told you once you tell me the mass and tell me where my planet is, I can tell you how much gas they should accrete. So we calculate how much gas you accrete. Then you could follow the evolution of that gas, this envelope, over time. Right? If you're big enough, you keep it. If you're not quite big enough, you start losing it. And you can ask, what does this radius distribution look like after a few gigayears? And you do get this green line. So initially, actually, most of them start off here because they're similar in mass. But you see, over a few gigayears, you get so much mass loss, basically from the cooling of the envelope and the core underneath, that you convert some of the large radii planet into those small ones. They have a small radius, and these are basically naked cores. So the data we have is actually consistent. We can actually understand this exoplanet observation just in the context of accretion. And it's really interesting because it means that all this big population of super-Earths really kind of formed as one population. You don't need to have one that's been rocky from the beginning and one that was gaseous from the beginning. You can really convert those gaseous cores into rocky, barren, and these gaseous, the planets with these gaseous envelopes into these rocky cores. And I should say that this was also exactly the same trend has been recently also been found for our M dwarfs. So it really shows that this is robust to systems independent of what host stars they have. Okay, we can look at the same results in a different way. Now we can plot, so just before I only plotted radius explicitly. Here we can plot mass as a function of temperature. And I told you, so if I'm massive enough and cold enough, I should keep my envelope. So everything above this line here, these planets should keep their atmospheres. And everything that falls below this line, with this Bondi written on it, should basically be stripped of any hydrogen helium that these objects had. And we can plot on top of this the actual population of extrasolar planets that have both mass and radius measurements. And it looks like this. So here I color-coded the points according to how much envelope fraction you can infer. And you can see that, indeed, all these black points, which are consistent with having no gaseous envelope at all, fall below this line as expected. So again, I think it really shows that these planets most likely really all formed with a gaseous envelope that then was just simply couldn't be retained by the planets that were too hot and too low in mass over gigayear timescales.
Are the couple of data points that are above the line that are black, are those just maybe in young systems? Or
That's a good question. So I think the only one that I would be concerned about is maybe this one here, because here the error bars are so big. You know, I'm not sure. Even this red one, but it is only marginally, it's still less than 1%. Yeah. So ask me again at the end. So basically, this may be our one or best candidate if you are looking for a truly rocky analog. This may be the planet we want to look at. Because one of the questions is, if you want to study Earth-like analogs, do you want to study planets that had gigantic hydrogen helium envelopes and they were stripped over time? You could still maybe eventually arrive at conditions similar to Earth. Or do you maybe want to first look at planets that probably in their formation were really similar to the Earth from the beginning, in which case this guy down here would be your best bet. Yeah, we're currently actually writing a paper about what we can truly say about some of those outliers, because there may be actually some of our most interesting planets to look at. Yeah. So I can draw a few more lines on this. So there's also additional mass loss due to UV and hard X-rays from the stars when they're really young in their formation. And although I think it's important, I don't think that dominates the mass loss, and I don't think that's responsible for this clean trend, because the strength of this XUV radiation varies a lot from star to star, and should also be different from M dwarfs to G and K stars. And we do see this nice trend very clearly for both systems. And so I think this mass loss due to cooling is probably the likely explanation for that, because it only depends on the volumetric luminosity of the star, and that's much more uniform across these samples. Then, so I colored these points here, and so this blue line here tells you how big of a core should have accreted 5% in terms of gas mass, and you can see that that works very nicely if you look at those planets with envelopes that are 5 to 10%. However, we can take this a step further, right? You say, okay, I can draw a similar line for planets that accreted, say, 2% or 1% of gas, and then I would draw this red line down here. And you see that my red points live up here in this region, which means that they actually, it looks like a given core mass should have accreted much more gas than we see here, and that this cannot just be explained by loss alone. And furthermore, this all seems to be jumbled here. There's not a clean separation, right? I told you there was a simple prediction between mass and temperature of how much atmosphere you should have accreted. And there does seem to be more diversity in the planet sample than you would predict just from accretion alone. So before I continue, let me just quickly summarize this. So during accretion, as planets form, they don't get to keep all their envelope. They actually shed the outer layers, often of the order of 25 to 75%, during the dispersal phase. During that time, though, they also shrink to radii that are comparable to their core radius. So they actually shrink to pretty small radii rather quickly, which is extremely different from what people naively do when they just look at the thermal evolution models of planets, where they give them some initial random condition within really arbitrary large envelope radius. Then if you have a light atmosphere, meaning less than about 5% of the total planet mass, this entire atmosphere can be lost over gigayear timescales. However, if you have heavy atmospheres, those atmospheres can just cool and contract, and you can get a nice planet like Uranus and Neptune or some of those super-Earths. So in what's left, I would like to quickly go into why are they so different. So I told you it's a little bit surprising that given a given planet mass and a given temperature, I do see a big variety in how much gas these planets have accreted, which is different from what you expect by a simple theory of gas accretion. And to drive home this point of diversity more, I made this plot here that shows the bulk composition of these planets as a function of mass. So here is the mass of these planets and Earth masses. And on the y-axis here, I just have bulk composition. And you can see that there's a huge spread. So even if we pick a planet of a given planet mass, say 7 or 8 Earth masses, the inferred bulk density is from, 0.7 to almost 20. And this is really surprising, at least to me. Because although in our own solar system, we do have a big variety in terms of bulk composition, right? Our Earth is 5 grams per centimeter cubed in density. Saturn is 0.7. But if we pick a given mass, they're all the same density, right? Earth and Venus are essentially identical. Uranus and Neptune have the same density. And so do Jupiter and Saturn. So if you tell me a given planet class, they essentially have an identical density. And that's actually why when I plot Uranus and Neptune here, they both sit on top of each other here. Or Earth and Venus sit right here. But that's not true for the exoplanets. A given planet mass, we pick one mass, you have more than an order of magnitude spread in the bulk composition. And again, of course, it just means that some of them have huge hydrogen-helium envelopes, and some of them have none at all. And I already told you that it's not the whole story. It cannot be the whole story that you have loss as a result of accretion as the disk goes away in photo-evaporation. Because we see those trends in the plot I showed you before, and maybe even more clearly you can see it here. Here I plotted the same bulk composition as a function of stellar flux, so basically function of equilibrium temperature. And you can see that there's a big region missing here. And this is almost certainly because there used to be planets down here, and their envelopes were stripped, so they were converted from low-density planets into high-density ones. However, if you go further away from the star, you are less affected by that, and you see you still have the full spread. So something is giving you this big variety in bulk composition. What could that be? Well, I think what's happening is this. So you have these multi-planet systems forming, and we know they form in the presence of the gas disk. So as the planets are forming, they are interacting with the gas disks, and because of an exchange of torques between the disk and the planets, you typically get inward migration. So the planets form somewhat further out in the disk. They're migrating inward, and as that happens, you usually have convergent migration, and you start to trap planets in what we call mean motion resonances, where you have a small integer period ratio between neighboring planet pairs. And you set up nicely, tightly packed planetary systems that way. And this would actually explain why we have so many tightly packed systems in the Kepler sample. But then what happens next is that the gas disk goes away. So my nicely set planetary system that's shown here with 8 planets, it migrated from further out. I trapped them all in mean motion resonances. Now, as the gas disk goes away, the system eventually becomes dynamically unstable because I was able to pack them tightly because the gases was doing a lot of damping, keeping my planet stable. The gas has gone away. The planets start to perturb one another. And what happens? You again get orbit crossing, and you get 1 or 2 collisions. You merge these 8 planets into 3 or 4, and then your system can settle back into long-term stability. So people have done numerical simulations where exactly found this. They typically find 1 or 2 collisions after the gas disk has gone away to stabilize these systems. And I think this may also be the explanation why when we look at these planetary systems today, and if you look at the period ratio distribution, that most of the planets that we see today are not in mean motion resonances. They don't have a small integer ratio between themselves and their nearest neighbors today. But this is not so surprising if you really did have these instabilities and late collisions, because of course, after that, this would destroy any nice resonant chain that you had. So, but the collisions not only give you long-term stability and will not only break the resonances, the collisions, of course, will also modify the bulk composition of the planets. And that's what we looked at. So what we looked at is basically if you have a giant impact between 2 planets or planetary embryos, how much of the atmosphere do you lose? And it's a beautiful physics problem because you can do it almost entirely analytically. You get self-similar solution of the second type that you can, at least for the plane parallel case. And the best thing was, once we realized that, is I didn't even have, it sort of, the problem had already been done because it's been studied in actually many connections, but in astrophysics first in the context of thermonuclear explosions. So basically what happens when you have a giant impact, the velocity of the impactor is sharply decelerated. You convert all this kinetic energy into heat and really high pressure, so you get something like a point-like explosion, and then we can do the shock problem. And so we have a strong shock that propagates to the entire planet, and then that shock launches another shock at the planet-atmosphere interface, and then we calculate how much atmosphere you lose by simply asking the question, what fraction of the atmosphere gets accelerated to velocities above the escape velocity, and we have the answer. I should mention this also, I call this the mechanical part of the loss. There's also a thermal part because you also heat the system a lot, so you can lose a lot of the envelope this way in addition afterwards. Okay, so basically, you can calculate the atmospheric mass loss. Once you understand the problem, I think it was fairly straightforward. So we did this analytically. You can see that the total mass loss, which I'm showing you here, is a function of the impact of the momentum of the impact. Consists of 2 components. There's parts on your planet where the velocity, even at the atmosphere planet base, is high enough that all the atmosphere above that point will be lost. And there will be places on your planet where the velocity at the base is not quite high enough, but then as the shock accelerates in the atmosphere because the density goes down, you reach an escape velocity slightly higher up. So you have parts on your planet where you can have complete loss, and you have parts of your planet where you may be able to keep the lower layers, but only lose the upper layers. And so you can add these 2 mass loss curves together, and you get something like this. Of course, you can also do this numerically, which of course we did as well. You can, of course, play around a little bit with the envelope structure, but the overall result is very similar. So in a nutshell, basically, is that if you have it in a single collision, you can easily reduce the envelope to core mass ratio by a factor of 2, maybe quite a bit more, depending on the exact collision that you're looking at. And so this means that in many cases, you can change the bulk densities by factors of 4 to 10, and therefore a single collision can change the total spread or the bulk composition of your planet sample significantly. And so in a upshot, we think that this large diversity and bulk density of the planets is a signature of having 1 or 2 late collisions in these systems and that basically the ones with the really low densities are the ones that were the lucky ones that didn't have any giant impacts, and that the ones up here were the ones that had a lot of their envelopes stripped. And I think this is a particularly nice and attractive explanation for systems that reside on multiple planet systems, like Kepler 11, 20, 36, and so on, where you have 2 planets or 3 planets that are separated by less than 0.1 AU, and yet one planet, and they have the same mass. Yes, one planet is totally rocky, and the other one has a giant gaseous envelope, because I think it'll be very challenging to explain that any other way. Okay, thank you.
What's the mass ratio of colliding objects that you considered?
We considered many, but they're all in the giant impact range. For the analytic part, you sort of, all that matters was the impact momentum, so you could actually trade off the impact velocity for the mass. So you could get a similar result for an impactor that has twice the velocity and only half the mass, and vice versa, if that makes any sense. Yeah.
But would it be, the moon colliding with something like the Earth? Is
Yes.
that sufficient? Or?
Yeah, that's not sufficient. Thank you for the question. Okay, so the moon forming impact is not sufficient to eject, to lose a significant fraction of the Earth's atmosphere. Our work, and actually some previous work that looked at that earlier, you find the typical mass loss fraction is only 5%, 5 to 10%. So this is actually really interesting because it means that had the Earth had a hydrogen-helium envelope, just from the moon, the canonical moon-forming impact would not have been enough to lose that. However, I think the reason why the Earth doesn't have a hydrogen-helium envelope and why we don't have any good evidence that it had in the past, we don't know for sure, is most likely from the fact that I told you that the Earth most likely formed from a series of Mars-sized embryos. And those embryos would have accreted much less hydrogen-helium because they have lower gravity, they can hold on to much less. And if you then have a series of collisions, I think you can actually lose those. But you really need the series of collisions, and you need those small initial embryos. Because once you have something as big as Earth, and then try to stick a hydrogen-helium envelope on top, you will actually keep it in a moon-forming collision. Yeah. Yes.
What stage you call it a planet?
Ah, very good question. I don't know. You know, when is a planet a planet? I mean, we decided Pluto is not a planet anymore. So
Many of the things points you put in your first diagram,
yeah.
diagram, the mass versus radius, then they may not really be planets. And because what worries me about that diagram is the bias. Because
Well,
the planet size is small.
but they're all bigger than the Earth. I mean, you can decide for yourself, but so far I haven't had anyone who had trouble calling something the size of the Earth to be a planet. So, the official definition is it has to be large enough to retain hydrostatic equilibrium. So I think these are all large enough that they will satisfy that. So I think eventually we will reach a regime. There are some people who think they indirectly detected asteroids or comets. So yeah, there probably wouldn't be planets. It's not impossible that, but most of these, they're at least half, most of them are bigger than the Earth, and almost all of them bigger than half the Earth. So you would still be easily in the regime where you would, you're not Pluto yet. So from that point of view, it's probably okay.
And then the second question I have, what planets like Earth are so rare?
We don't know yet if they're really that rare, right? Because we have really struggled to find Earth-like planets right now with the technology we have.
Because of the size? Or
Yeah, because of the size and the long orbital period. So it's a square root of n problem, basically. In the transit method, right, the reason why we could find smaller planets down here is not because they were around better stars or something. It's because something on a 1-year period, we get 365 transits in 1 year. And we just stack all of them together, and then you get a better signal to noise, so you can pull out smaller planets. You can be sure that you actually saw your planet compared to something that's an Earth at 1 AU. And so right now, basically, if Kepler could have continued for another 10 years, we would have pushed this limit down here. Oh, by a factor of 3 and a bit. But basically, it's a square root of n problem. And so we just have to be patient with the 1-year periods. So you can either look for planets around brighter stars, where you just have intrinsically better signal to noise, or you can just wait for longer and build up a large enough number of transits, and then you can push this limit down. But we don't yet truly know how rare the Earth is. I mean, we make estimates, right? Because you can use this and do some fancy statistics and can say, okay, I missed all those, I should have found these. But the number that people quote is like 10%, maybe 20%, but the error bar is humongous because it really depends on these assumptions you have to make and extrapolations. That the data hasn't really given us the answer yet. Yeah. Yeah, tests will help. Well, actually, so tests will not help and help. So tests will help because tests will help us finding planets around nearer and brighter stars, so you can study those better. However, TESS only looks at a given patch of sky for 30 days. So it won't find the long period ones on a 365 days. So for me, this is really heartbreaking, but I guess some people are okay with it. So yeah, because I would love to know what's further out, right? But anyways, I didn't get to change that. There was, yeah?
Just a quick follow-up. So you said that in order to be on this, it requires seeing it 3 times.
Yes. Mm-hmm. Yeah.
Did they try to relax that to 2? Because that would give you an indication.
Right.
If you're getting more usage.
Yeah, that's right. Yeah, people have tried that, and there are a few Jupiters reported even just with 1 transit. So you can probably be a little bit more certain that this is real because the duration is so much longer. You have a little bit more data. So yeah, it's just the statistics are not that strong. So actually, the strongest constraint we have for the longer periods come for Jupiter from the radial velocity, and actually for Neptune and Uranus type planets comes from microlensing surveys, because they basically give us the strongest constraint at like the 10 AU right now.
Okay.
Okay, what?
I was thinking a little bit about your last plot,
Mm-hmm.
which was the 1 versus temperature.
1 versus
What
temperature.
temperature is that?
That's the equilibrium temperature. So that's basically the temperature you would expect from the star at a given semi-major axis.
Right, but you were saying
Mm-hmm.
it was losing its atmosphere because of core,
Mm-hmm.
the core
Cooling, yeah.
cooling and the heat from the core
Yes,
blowing off the atmosphere.
that's right.
So,
You want to know why the temperature figures in that?
yeah.
Yes, I'll tell you. It's because it sets a temperature at the radial convective boundary. So when you look at the structure of the envelope, the outer layer is isothermal. So, but then the temperature at the radial convective boundary is set by the equilibrium temperature from the star to very first order. And so the temperature there sets both the rate at which you cool and the rate at which you would accrete gas if you would still do that. And that's why the temperature enters there. Sort of your outer boundary condition, if you wish. Yeah. It also tells you sort of how big the temperature gradient is between the core and the outside. Yeah. Basically, your core couldn't cool to a temperature below that. Yeah. Very good question.